In this video, we're going to start investigating the photoelectric effect, which is an interesting phenomena that occurs when, if you shine light on particular types of metal, current actually flows out of the metal, or through the metal, I should say. Einstein actually won the Nobel Prize for explaining the photoelectric effect, which is a little bit of, it's a tidbit of information most people don't know. People assume he won it for relativity, but he actually didn't. He won it for explaining the photoelectric effect. To give you a little background on why this is so important, for a few centuries before this, people had been arguing over whether or not light was a wave or a particle. Isaac Newton, who was a big deal, and did a lot of work, not only with gravity and the motion equations that we know, but with optics. He worked with light a lot. Isaac Newton was of the opinion that light was a stream of particles. You can think of it kind of like raindrops falling on an umbrella, right? If rain is falling all around, what do we see under the umbrella? We see this little circle where the ground is dry and everywhere else it's wet. Well, Isaac Newton reasoned similarly to say that light, if you have rays of light here, casts a shadow. And so he used reasoning similar to that. I'm not saying he thought exactly of this, but he used reasoning similar to that to postulate that light was actually made up of a stream of particles, much like rain is made up of individual raindrops. People disagreed with him. People agreed with him. It was most notably Christian Huygens disagreed with him. Huygens was a proponent of the wave nature of light. He thought that light was a wave. And people actually went back and forth over that for a few centuries. And there were certain times when the wave theory had dominance and the particle theory had dominance. But about the time of Einstein, most everyone was considering light to be a wave. And that is basically because of the Young's double slit experiment we looked at in the last chapter, where if you have light incident upon a barrier with some slits in it, and then you have a detector screen over here, what you get is light diffracting through these openings, interfering with the two sources interfere with each other, and you get the interference pattern over here. And what I believe I said when we went over that, if you're in my class, is that this is only exhibited by waves. Interference is a wave phenomenon. So everyone said, yes, light is a wave. It's definitely not a particle. Good job on everything else, Newton, but you were wrong about this one. Fair. And so we kind of figured it was settled. However, there is a certain effect that that people were having trouble explaining. I'm going to give you sort of a very crude rundown here, although there's more details in your textbook, again, if you're in my class. Imagine, if you will, that you have a piece of metal here, and you are irradiating that metal with a certain type of light. What type that is, what type of metal it is, kind of depends, but you are irradiating that metal with a certain type of light. What you find then, if you put an ammeter here, and I should point out this is going to be connected to another plate. If you have an ammeter, is that you register a current when you irradiate this with light. Now, we know what currents are, right? And back when this was explained, they knew what currents were. They knew that currents are movements of electrons around. And so and we knew that electrons are bound up into atoms. So what has to be happening here is that the light is bringing in energy, then dissociating the electrons from their atoms so that they're free to move around the wire. And that's easily explainable if you remember that a wave is just a transfer of energy without an associated transfer of matter. So the waves are coming in, this is what they thought the waves were coming in, exciting the electrons and then sending them down the wire. Now, there were some details that actually don't match up with that. I'm just going to go over a couple here. One detail that did not work was that we can measure the kinetic energy of the electrons that are flowing down the wire. The kinetic energy, I should say this, did not change when the intensity of the light changed. So if light is acting like a wave here, the intensity is going to have to do with the amplitude. And that definitely has to do with the energy. We know that energy varies with frequency, but it also, more importantly here, varies with the square of the amplitude. And so if we increase the amplitude, we just make our wave bigger, we would expect the electrons that it knocks out to just get more energy from that wave and to be moving along the wire with increased energy. Turns out that doesn't happen. Interestingly enough, the current does vary with intensity. So if you have a light source shining on this metal and you turn up the intensity, you get more electrons, but the electrons themselves don't change. Their average kinetic energy actually doesn't change. That was actually very strange because, again, if we expect this wave coming in and imparting energy to the electrons, we expect the energy that is absorbed by the electrons to just increase, and so we don't expect more electrons to move down the wire. We just expect the ones that are moving to have a higher energy. We also found this. There is a cutoff or threshold frequency for the effect. That is, if the frequency of the light drops below a certain frequency, a certain threshold, the current stops flowing. This is also not understandable by treating light as a wave, because if you have a lower frequency, yeah, it carries less energy, but you expect the wave to be able to impart little by little the energy to the electrons, and so that sooner or later they've absorbed enough energy to be able to move along. But that's not how it works. There are other things that didn't fit in. I'm just going to deal with these three, but there are actually a total of 5 questions that didn't match up with characterizing light as a wave, and really nobody could figure this out. This is a really important issue at the turn of the last century. Well, enter Einstein. In 1905, Einstein produced 4 papers, any one of which could have won him the Nobel Prize. It was called his miracle year. Special relativity was included in there. Photoelectric effect was included in there. The theoretical foundation for the laser in 1905 was included in this group of papers. It was an incredible year. But the one for which he won the Nobel Prize explains this. And Einstein very simply said, you know what? We cannot consider light, for this thing, we cannot consider light to be a wave. We have to consider it to be a particle. Now, before we get into how this fixes this, if this is true, notice how weird this is, because we've already said that light is the proof positive that light is a wave is that it interferes with itself. It shows an interference pattern. Therefore, light is a wave because only waves do that. And we rejected the particle nature, but if this turns out to be right, we are in a really strange situation, because the interference pattern is unexplainable if light is a particle, and the photoelectric effect turns out to be unexplainable if light is a wave. And so we have run up against this strange thing that we never find in the macroscopic world, which is that light can either be considered a wave or a particle, depending on how you look at it. Now, this is, again, strange no matter how you slice it. So let's see if this matches up. So Einstein said that the energy of he called these photons, particles of light, and he said that the energy of an individual photon will be given by hf. We saw h in the last video. That's Planck's constant. It's a very, very, very small amount. And the units are joules seconds. Remember that the units of frequency are 1/seconds. We usually call that a hertz. But when you get a joule second times a 1/2, you're left with just a joule. And so this is the energy of an individual photon. This is a very small number, so the energy of one photon is very tiny. But if this is true, this turns out to explain these really, really, really well. What does that mean here for number one? How does that explain number one? Well, if the intensity increases, what that means is that the number of photons increases. Right? Now, think of it. If each of these photons is giving all of its energy to one electron, so here's an electron, here's a photon, that's usually how they're symbolized. It comes in, it's absorbed by the electron, or it has a collision, however you want to think about it. The electron then goes, it heads off with a certain amount of energy. That energy was absorbed by the photon, or the energy absorbed was equal to the energy of the photon. So this electron now has a certain energy, right? So if I increase the intensity, I increase the number of photons, which means I don't actually change the energy of each individual electron. Each individual electron has just absorbed one photon, and so the average kinetic energy of this thing is the same as it ever was, which explains this. This explains that the kinetic energy, the average kinetic energy of the electrons, doesn't change when you increase the intensity. As it turns out, this also explains number two, the current, and I really shouldn't use I for both of these. Current, I'm going to use I for intensity here. We know that I is current also. It's an unfortunate thing. So let me just remind you of what this is. This is the intensity. But this also explains number two, the current does vary with intensity. Well, what is current? It's a movement of charges. So the more current means there are more charges moving. Well, if I increase the number of photons, what I've done is increase the number of electrons. Those electrons each have the same amount of energy as they ever did, before I increase the intensity, the ones that are moving. But now I just have more moving because I've put in more photons and knocked out more electrons. So this actually explains 1 and 2. It explains number 3. If you've taken chemistry class, if you haven't, this will be your introduction to it, but you'll see a lot more of this when you take chemistry classes. An electron that's bound to an atom has what's called a binding energy. Your book uses the symbol Be. I'm not used to that symbol. Most textbooks use the symbol Phi, and they call it the work function. Whatever you want to say. However you want to express it doesn't really matter to me. But it's a certain amount of energy that it takes to remove the electron from its host atom. So a little bit of energy is not going to remove the electron. In fact, the electron doesn't even notice that it's there. But if you put in the right amount of energy, the electron can absorb that energy and it's removed from its host atom. Of course, you don't have to remove it. There are lesser amounts of energy that will bump it up to different energy levels. But you have a certain energy that it takes to remove the electron from the host atoms called the binding energy. That actually explains number 3, because if the energy of the photon varies as frequency, if you drop the frequency too low, you're actually beneath the binding energy of these electrons, and none of them leave their host atoms. And so you get no current. But if you go above that threshold, you start to knock them out of the atoms, and then they're able to move around the wire, and they form a current. So, and the other 2 reasons that the waves are problematic are also explained by this. I'll let you look in your textbook for those if you want. But basically, Einstein completely explained the effect by positing that light has to be at least acting like a particle here. Well, one of the things we go by in physics is if it's acting like something, it is something. And if an explanation satisfactorily explains a problem, that explanation is right. So what we're left with is this really strange idea that light, if we go back to our original question, is light a wave or is it a particle? We have to say a resounding yes to both of them. There have been people, maybe tongue-in-cheek, who have introduced the word wavicle. Whatever. You can use that if you want to. But the idea is that light is not something that we can really draw a good analogy for by our macroscopic understanding. When we think of a particle, we think of, usually we think of little BBs flying around, or maybe little rocks, or little bowling balls. When we think of a wave, we normally think of a sound wave or a water wave. And so this is not an original thought. I saw a physicist named Leonard Susskind talk about this. Imagine the last time you were at the beach and you look out at the ocean and you see waves, and then look down at your feet and you see little particles of sand, and then somebody comes along and tells you, well, those waves out in the ocean, those are actually particles. And those little things of sand at your feet, well, those are actually waves. I mean, you would look at him like he's an idiot. Like, what? What are you talking about? So it's really difficult to find a macroscopic analogy for this, but it turns out that waves and particles are both characterizable, or both characterize what we mean when we say light or electromagnetic radiation, to be more specific. It can act like either one, and will do so depending on the application. So there's some things we can explain by invoking the wave nature of light. Diffraction is one of them. Reflection is another. There's some things we can explain invoking the particle nature of light. The photoelectric effect is one of those also. So we're kind of through the rabbit hole here. Or down the rabbit hole, maybe through the looking glass, even better. We're seeing something new. This is different than what we've understood about the universe so far. We're going to continue to investigate this quantum mechanical functions. They get weirder, but this is a good place to start.